questions from yous guys. Dan.
You do number 9.
Can we do number 9? Sure. So number 9 was the cube root of 25 times cube root of 320 plus the cube root of 3645 minus the cube root of 625. So obvious to see right away that we can't add or subtract these radicals as currently written, right? But it's possible that maybe I'm able to add or subtract these after I do a prime factorization and reduce the radicals a little bit. So I have to check that. So 25 is 5 squared. Uh, 320, well, that's 2 and 160. That's 10 and 16. That's 2 and 5. That's 4 and 4, which is 2 and 2. So I have 1, 2, 3, 4, 5, 6 2's and a 5. 3645, that's 5 and 729. And that is 3 and 243, which is 3 and 81, which is 9 and 9, which is 3 and 3. So I have 1, 2, 3, 4, 5, 6 3's, and then a 5.
Wait, how did you get 26.5 if you add the 1610?
How did I get 26.5?
Oh, sorry.
Yes, that's okay. And then the last one, 625, is 5 and 125, which is 5 and 25, which is 5 and 5. Is everybody okay with the prime factorizations that I just kind of buzzed through there? Okay. So next thing I need to do is I need to reduce these radicals. So I'm going to just keep that cube root of 5 squared out front. If I look at the first radical, I notice that the exponent on the 2's is bigger than the index, so I can do an exchange there. I know the number of times that 3, the index, goes into 6, the exponent, is 2 exactly, right? There's no leftovers. So I can take 2 2's out, and I have just this cube root of 5 left. Similar thing is happening here. I can take 2 3's out and have just the cube root of 5 left. And the last one, if I compare the exponent to the index, 4 is bigger than 3. So I can take 1 5 out, and there'll be 1 5 left over inside the radical. Okay to hear, Dan? Okay? So 2 squared is 4, 3 squared is 9, and then 4 plus 9 minus 5 is 8. Okay there? Now let's multiply this in. So when I multiply those, I end up with the cube root of 5 to the 3rd. And I can reduce that radical, right? So 5 to the 3rd, I can exchange all 3 of those 5's underneath for 1 5 on the outside. with nothing left in my radical, so I can just forget about the radical. And 8 times 5 is 40. Annalise.
For number 6, I got like, I got like 4, and then like the square root of 7, like the cube root of 7, and then 18.
Okay, so hold on a second so everybody else that might be interested in 6 can follow along. So I'm just going to write down the problem real quick, and then I'm going to write down what you wrote or what you got and let you know if these intermediate steps were right or wrong. Okay? So just so that everybody else can have this conversation along with us. Is that okay?
Yeah.
Okay. So this first one, you said you got 4 times the cube root of 7, which is good.
And then minus 18.
Oops. Good. 18 cube root of 7. That's good.
And then minus 45.
Good.
And then I got 14 cube root of 7. But then from there I got negative 15.
So you got negative 14
Yeah.
cube root of 7. Okay.
And then I got,
Did I just add wrong here? Is that what you're saying?
I don't know. I didn't know if I did.
So then it should be negative 59. I wrote negative 62. Yep, that's just wrong. So, oopsie-daisy. Just FYI, guys. Bless you. You're welcome. That's number 4. So it should have been negative 59 cube root of 7 instead of negative 62. I don't have a good excuse there. You know, sometimes we just make mistakes, you know. Thank you, Annalise, for helping point that out. No, I mean, if you have a question, like, it's not what I got, I wonder why. Sometimes I make mistakes too, it's okay. You know, I'm glad you followed up. For either reason, whether it was because you did it wrong or I did it wrong, somebody did it wrong. Might as well find out who, right? So thank you. Any more questions on this sheet? Jack. Okay. Okay, well, if that closes things off there, how did this go for you guys in general? Was that okay? If you're able to reduce radicals, it should have been pretty easy. If the reducing radicals part is still hard, then certainly this would have been challenging. But if you can reduce radicals, the adding part at the end is easy. And just getting it into the form where you can do the adding, that's maybe a little tricky. Today we're going to continue talking about simplifying radical expressions. This is our 3rd lecture on this. And our goal today is going to be dealing with things like this. So our goal is to figure out how to multiply things together that have different indices on the square roots. Or on the radicals, I shouldn't say the square roots. You guys knew what I meant though, right? That's our goal, is to figure out how to do this. Now I'm going to take the long way to answer this question. I could answer it really quickly for you guys, but that's not very much fun because I think it's important you understand like how I'm doing some of these things, like the how. So what we're going to start with is a new way to define a radical. So this new way is going to be to rewrite a radical as an exponent So this is like the exponential form for a radical. So let's say I want to rewrite the cube root of 7 to the 5th in exponential form. How would I do that? So 7 to the 5/3. Everybody okay with that? So you have to remember that the index for the radical is the denominator in the exponent. Is kind of the trick, right? So what if we have 2 to the 7/8 and I want to rewrite that in radical form? What kind of radical is this? What is the index on the radical? It's 8, right? So this is an 8th root of what number? 2 to the 7th. Is everybody okay with this definition and how to convert back and forth between radical and exponential forms? It's pretty easy, right? Not a lot to do. You just have to remember that the index is the denominator of the fraction and the exponent is the numerator of the fraction, right? Okay. So why is this helpful? Because we have a whole boatload of rules that we can use for exponents. So if I multiply two exponents together, like a to the m times a to the n, what does that result in? Yeah, a to the m plus n. Right? So for example, if I have 2 to the 3rd times 2 to the 5th, that's going to be 2 to the 8th. Right? Because I had 3 2's and 5 2's, so altogether I'd have 8 2's. Is that everybody okay there? Okay. So what if I have a to the m to the n? If I have an exponent of an exponential. Yeah, it's going to be multiplying. So for example, if I have 2 to the 3rd to the 4th, what that means is I have 2 to the 3rd 4 times, right? So I have 3, 6, 9, 12 2's. Everybody okay with that idea? And notice that 3 times 4 is exactly 12. That's why that works. I'm going to erase those because it starts to look like a fraction now if you went back and looked at it. That doesn't make a lot of sense. Cool? So far, so good? Tommy?
Why don't you multiply the 2's together? Like, you multiply them into 3, so you go like 4, 6, 8.
How come I don't multiply the
Like
twos?
you just do the exponents then?
Well, yeah, like if I did 2 times 2, that's the same thing as 4. Or I could write it as 2 squared, right?
Yeah.
And just by adding the exponents.
Okay.
So it's the same idea here. We don't want to multiply the bases together. We want to keep everything in a factored form because it makes it easier to kind of reduce our radicals.
Mm-hmm.
Does that make sense?
Yeah.
Okay. Okay. Let's see. So the next one, a to the 0 is equal to, nope, 1. That's assuming that a is not 0. If a is 0, what's 0 to the 0 power?
0.
Undefined. It's just like dividing by 0. So for example, 3 to the 0 is 1. 1. Okay, you want to see why that works?
Yes.
Okay. So if I have a to the m and divide it by a to the n, how does that happen? We subtract. So, for example, if I have 2 to the 5th over 2 to the 3rd, what would I get then?
5 minus 3.
Okay, 2 to the 5 minus 3, or 2 squared. So, Elena, to your aside, if I had 2 to the 2nd over 2 to the 2nd, I would get then
You want the whole answer? 2 to the 2nd minus 2, and then you get
2 to the 0, which is 1, because I know if I have like 4 over 4, that's the same thing as 1, right?
Yeah.
That's why anything to the 0 power is giving us 1.
Okay.
Does that make more sense now?
Yeah.
So I needed this other rule to kind of justify that, why something to the 0 is 1. And now you see why there's a problem if I have 0 to the 0, right?
Mm-hmm.
Because if I have 0 in the denominator of my fraction, I know that that's bad news. That's undefined. How about a to the negative n? That's the same thing as 1 over a to the n. So for example, if I have 5 to the negative 3, that's just the same as 1 over 5 to the 3rd. Does this property make sense? Can you see why this works? As just a little aside, 1 over a to the n is the same thing as a to the 0 over a to the n, because anything to the 0 power is 1, right? And if I use my subtraction property, that's the same thing as a to the 0 minus n, which is just a to the negative n. So that's why the negative exponent is making a fraction, right? Maybe not super obvious why that's happening initially, but that's what's going on there. Okay. Does everybody feel okay about these properties here? So if we go back now to this example that we had at the beginning, where we had the square root of 2 times the cube root of 2, the way I'm going to deal with this is by rewriting these as exponentials. So what is the square root of 2 in its exponential form? So remember, that's the rule that we're using.
1 over 3.
So it's 2 to the 1 over 2. Very good. Where did that 2 in the denominator come from, Annalise?
The square.
Yeah, the index on the square root of 2 is 2, right? Okay. How would I rewrite the cube root of 2 then?
Times 2 to the 1 over 3.
Very good. Is everybody okay there? Okay. So if I multiply 2 to the 1/2 and 2 to the 1/3, we would add those exponents, right? To add two fractions, what do we need to have? A common denominator. What would the common denominator be between 1/2 and 1/3? 6. So what do I need to multiply 1/2 by to make that common denominator? Well, 3 over 3, right? Because it's got to be the same number to the numerator and denominator. What do I have to multiply the 1/3 by? 2 over 2. So that's going to be 2 to the 3/6 plus 2/6. Everybody okay there? And then how do I add the fractions together then once we have a common denominator? We add the tops, but the bottom stays the same, right? And now I can put this back into radical form. What would the radical be for this? What kind of root is this? What's the index here? 6. Very good. Of 2 to the what power? 5th. Is everybody okay with that? So what these properties allow us to do is allows us to do problems where we have mixed radicals. We can now pull those apart and put them in exponential form and combine, square roots and cube roots and things together via multiplication, which is pretty nice, right? We can also just worry about problems that are in the exponential form. So let's look at something like that. So we're just going to do a bunch of examples now. Okay, let's say we have the cube root of 12 times the square root of 48. So I would start something like this the same way we have been. And I would start by doing my prime factorization. So I have a cube root of 2 squared times 3 multiplied by the square root of 2 to the 4th times 3. Everybody okay there? Okay. I'm going to now convert these into exponential form. So this piece, the 2 squared, becomes 2 to the 2/3. The next piece becomes 3 to the 1/3. And then I have 2 to the 4 halves. And then 3 to the 1/2. Everybody okay there? Good. Notice that 4 over 2 reduces to just 2 squared. If I have no more fraction in my exponent, I'm going to move all that stuff to the front because it's no longer inside of a radical, right? Everybody's okay there? Once the denominator of that fraction goes away, it's no longer in a radical. So I'm just going to move those things to the front. Now the 2 to the 2/3 I can't do anything with. But I can combine the 3 to 1/3 and 3 to the 1/2. Everybody good there? And just like we saw before, to multiply or to add these two together, we have to make a common denominator, which means I'm going to multiply by 2/2 and 3/3. That's going to give me this. I just shortcutted through some steps since it was the same work as in the previous example. Is that okay with everybody? Oops. There's a 2 there also. Annalise.
And then the 1/3 came from the 3. So to combine them, do they have to be like the same number on like the
Yes.
like the 3? So
Yeah, we call this number the base of the exponent or of the exponential. And if we go back and we look at these properties, notice that we used the same letter here, right? You can't do 2 to the 3rd times 3 to the 4th and have that work. Okay? So, for example here, if I have 2 to the 3rd times 3 to the 4th, that is not the same thing as like 6 to the 7th. That is not true. Okay? Now, what you could do, what is okay, is if you have like 2 to the 3rd times 3 to the 3rd, that is the same thing as 6 to the 3rd. That is okay to do. Where either the bases have to be the same, and then you add the exponents, or the exponents have to be the same, and then you can multiply the bases.
yeah, because in the other homework, I think I did like the second one where they both do like add them together, but
This is the same thing that we're doing when we had like that's that same property going on right there. Does that feel okay? You're welcome. Okay. So good question. Again, like I am ecstatic to answer like clarification rules like that. Those are really important that you understand like what you can do and what you can't do and why you can do why it looks like I'm able to do it this one time and not this other time. Very important that you kind of get those things cleared up because there's a lot of rules going on here and a lot of like, oh, I can multiply these things together. Oh, no, you can't kind of things. And it's important you understand when you can multiply things together and when you can't because it's easy to make, get things kind of turned around and make a mess out of stuff. Okay, so very good question. All right. So the last thing that I'm going to do here, you see these two fractions. You see how the denominators are different. I want to make the same denominator here. What would the common denominator be between 2/3 and 5/6? Sixths, right? So I'm really just going to multiply this one by 2/2. And the reason I'm going to do that is because when I put this back into the radical form, both of those are 6th roots. so they can all go under the same radical. And I'm going to decline to multiply 2 to the 4th times 3 to the 5th because it's just a big gross number. If you wanted to type in your calculator, you could. That would be fine. I'm just going to leave it here, though, for the sake of this example. I don't think it provides any extra insight there to multiply those two things together. But this is where we would want to stop. Is that okay? Should we do some more? Probably, right? Do some more. Okay. Actually, let's make this 32 to the 7/3. Make it a little bit more interesting. Notice here, one of the problems is a radical and one of them is an exponential form. In order to do anything, we have to get them in the same form. Should I put them both in radical form or both in exponential form? Exponential is correct. Why would I want them both in exponential form instead of radical form? Yeah, well, if I put them in radical form, they'd be different radicals, and there's nothing I can do with that in radical form, right? One of them is a 5th root, the other is a cube root. So I need them both in exponential form because there I can manipulate things. Everybody fine with that idea? But before I do that, let's do the prime factorizations. In the interest of time, I'm just going to write down what the prime factorizations are here. You could check yourself if you wish, but I promise you that those are correct. Is everybody okay there? So the 5th root of 2 to the 8 turns into what? Good, 2 to the 8 fifths. And then how do I do 2 to the 5th to the 7/3? Yeah, so here I would multiply, right? This is 2 to the 5th times 7/3. And to multiply fractions, I'll just think of 5 as 5/1. So we're going to multiply the numerators together and then multiply the denominators together to give us 35/3. Okay? So, can I multiply these two exponentials together? Yes. Why can I do it? Because the bases of the exponentials are the same number. Since both of the bases are 2, I can multiply these together and get 8 fifths plus 35 thirds. In order to add those two fractions, what do I have to have? Common denominator. What would that common denominator be? 15 is correct. So what should I multiply 8 fifths by? How about 3/3? Because that'll give me a denominator of 15, right? What should I multiply 35/3 by? 5/5. So when I do that, 8 times 3 is 24. 3 times 5 is 15. 35 times 5 is 175. And then 3 times 5 is 15. So if I add these two together, I'm going to get 2 to the 189/15. Everybody, so far so good. Is this going to be a reduced radical? When I convert it back into radical form, would this be reduced? Okay, thank you. 199. Good. Thank you for double checking. I appreciate that. Again, if you think something looks wrong and I made a mistake, please let me know before we get too far into the problem, because it's easier to fix one number than it is to have to backtrack through a bunch of numbers to fix it. Okay. Back to my question that I was so excited to ask that I screwed up the addition. When I convert this to into radical form, would this be a reduced radical? You should be able to look at it right now and tell. The answer is no. And the reason is because the exponent is bigger than the index. Everybody agree with that? So what I'm going to do is I'm actually going to try to reduce the radical right now in exponential form rather than putting it back into radical form, because it just saves kind of a step to do that. To do this, all I really need to do is write 199 over 15 as a mixed number. The easiest way to do that is to use your calculator. So if I do 199 over 15 and then press the math, press enter, it's going to give me 13 and some change, right? Nope, I'm sorry, just enter. Just enter. I'm going to just subtract off the 13 to leave me just the decimal part. So this is 2 to the 13. And then the decimal part is going to be the leftover fractions. So here I'm going to press the math button and select the fraction command. And that gives me the leftovers. Is everybody okay there? On how I went from 199 over 15 to 13 and 4/3, or 4/5, 4/15. Okay. So now I'm going to use this property, but I'm going to use it going that direction. So right now, what I have is my a to the n plus m. Everybody agree with that? Looks just like it. You agree? So I'm going to use that property to write this as 2 to the 13th times 2 to the 4/15. Can you guys see that? Okay. So now when I convert this back into radical form, I have 2 to the 13th times the 15th root of 2 to the 4th. And again, if you wanted to multiply those things out, you could. It just, 2 to the 13th is a pretty big number. I'm not really interested in writing it all down. Writing it in exponential form is fine. But what do you guys think on that one? It's okay? Let's do another. Oh my goodness, guys, I'm so sleepy. Yeah, it would have been pretty righteous, my dude.
It says like 88% on the snow they calculated. It said 99%.
Yeah.
So I mean, it's not really that accurate, but I think still.
I think it's probably unlikely. I wouldn't count on it. All right. So what if we have? Actually, I'm gonna change this just a little bit. I'm going to make this 1/6. All right. Everybody good here? So I'm going to start the same way we did before with prime factorizations. So 32 is 2 to the 5th. 16 is 2 to the 4th. So there's that. Everybody okay here? So how do I do an exponent of an exponent like that? What do I do to the exponents? Multiply. What's 5 times 1/6? Good. And what's 4 times 11/6? Okay, 44 over 6, but that reduces, right? To just 22 over 3. Everybody okay here? All right. So now we have a bunch of options. And a bunch of our options of things we can do are going to run us around in like a big stinking circle. In general, when I look at this and I see the exponent on the bottom is larger than the exponent on the top, I don't want to do that division property where we subtract the exponents, because it's going to result in a negative exponent. Jack? I reduced the 44 over 6. Okay. So where were we? Okay. Many things I could do at this step. A lot of the things I can do at this step are going to be, let me say, unproductive. You might think to do the property where I subtract the exponent in the numerator and the exponent in the denominator. Right? Okay. The problem with that is if I do numerator minus denominator, I get a negative number. And remember, the exponent to the negative gives me a reciprocal. And then I'm back with an exponent in my denominator, which is the same thing as having a radical in my denominator that I don't want. Is everybody okay with that idea? Here's what I'm going to do instead. 22/3 is what as a decimal approximately? 7.3 repeating. What's the next whole number after that? 8. 8 is the same thing as 24 over 3. You guys agree with that? So I'm going to multiply the top and bottom of this by 2 to the 2/3. Why is that going to be helpful to me? Look at what's going to happen in the denominator. I've gotten rid of the fraction in my exponent. Can we all see that? Very nice. Now I don't have a radical in my denominator either, and I don't have to worry about that step. Everybody okay there? All right. I still have to do this, though, so I have 5/6 plus 2/3. I'm going to rewrite 2/3 as 4/6, though, so I have a common denominator. That's going to give me 2 to the 9/6, which is the same thing as 2 to the 3/2 when I reduce. Okay. And if I look here at the exponent, I have an improper fraction again, right? That's the same thing as having an unreduced radical. So just like we did in the previous example, I'm going to now rewrite that as a mixed number. 3/2 is the same thing as what? As a mixed number. 1.5, right? Everybody agree with that? Okay. So that's going to be 2 times 2 to the 1/2 over 2 to the 8th. And I can reduce here. Leaving me with the square root of 2 over 2 to the 7th. Again, 2 to the 7th is 128. If you wanted to multiply that out, you're welcome to do that. It's not incorrect. I'm just not going to do it for that one. Okay there? It's kind of a lot, right? Okay. I want to tell you guys, though, as far as the things we do in this second semester, being able to use these properties of exponents to kind of manipulate expressions and kind of move them around and change them around and combine things, this is maybe one of the more important skills kind of going forward that you're going to deal with in first or in second semester. First semester, it's the ability to deal with quadratics, to factor and solve quadratics. You use that all the time. Here, from second semester, it's this ability to kind of manipulate exponents and rearrange things and, you know, like change the forms and go in between. That's really kind of a useful skill going forward to have. So let's keep working on this. Let's do another example. Let's do another one where we end up with a fraction there. So let's say we have the 5th root of 448 over the square root of 96. So I'm going to start here by doing some prime factorizations. I'm just going to write down the prime factorization, though. You'll just have to trust me that this is indeed what it is. Do you guys trust me? All right, it's your funeral. I'm just joking. I'm trustworthy. All right. What should I do next? We need to rewrite these in exponential form. Oh, that's a 5 there. Excuse me. Okay. So that's going to be 2 to the 6/5 times 7 to the 1/5 over 2 to the 5/2 times 3 to the 1/2. Is everybody okay there? Okay. These we can combine together. You guys agree with that? How do we combine them together? If I think back, looks like this property to me. Do you guys agree with that? Okay. So what am I going to write here? I have 2 to the 6 over 5 minus 5 over 2. And then I still have this fraction multiplying 2. Everybody okay there? Okay. To multiply or to subtract 6/5 and 5/2, what do I need? Common denominator. What would the common denominator be? 10. So I need to multiply the first fraction by 2 and the second fraction by 5. Everybody okay there? So I'm going to get 2 to the negative 13 over 10 times that stuff, right? Ooh, what do we do with a negative exponent? Well, we had a rule for this, right? Yeah, we turn it into a fraction. That's correct. So I'm going to have 1 over 2 to the 13th. I'm sorry, 2 to the 13 over 10 times 7 to the 1/5 over 3 to the 1/2. And this is really, if I multiply these together, I can just put this all in the same fraction, right? Everybody good there? The last thing we need to do now, well, I shouldn't say the last thing. What we need to do next is to get these fractional exponents out of the denominator. Okay? What's the next whole number after 1/2? 1. What do I have to add to 1/2 to get 1? 1/2. So I'm going to multiply the top and the bottom by 3 to the 1/2. That'll get me a 3 to the first in the denominator, right? What's the next whole number after 13/10? Well, 13/10 is 1.3. So the next whole number after 1.3 is 2. Okay, so how many tenths do I need to add to 13/10 to get 2? 7/10. Everybody agree with that? So I'm going to multiply the top and bottom of this by 2 to the 7/10. So that's going to give me 7 to the 1/5 times 3 to the 1/2 times 2 to the 7/10 over 2 squared times 3. Two squared times 3 is 12. The last thing I need to do is I need all these fractions to have the same denominator. What would that denominator be? I have 1/5, 1/2, and 7/10. If I made a common denominator between them, that denominator would be 10. So I can turn 1/5 into 2/10, 1/2 into 5/10, and 7/10 can just stay 7/10. So that means we're going to have the 10th root of 7 squared times 3 to the 5th times 2 to the 7th. And that's where I'll stop. I'm going to stop here for today.